Hello, welcome back to Chill with Chill, where we're continuing to go through Runestone Academy's thinkcspy Python Basics training program, aka How to Think Like a Computer Scientist online book. So we're on section 5 of module 1, where we're learning more about programs. A program is a sequence of instructions that specifies how to perform a computation. The computation might be something as complex as rendering an HTML page in a web browser or encoding a video and streaming it across the network. It can also be a symbolic computation, such as searching for and replacing text in a document or, strangely enough, compiling a program. The details look different in different languages, but a few basic instructions appear in just about every language, such as input, which gets data from the keyboard, a file, or some other device. Output, which displays data on the screen or sends data to a file or other device. Math and logic perform basic mathematical operations like addition and multiplication, and logical operations like and, or, and not. A conditional execution checks for certain conditions and executes the appropriate sequence of statements. And finally, repetition performs some action repeatedly, usually with some variation. Believe it or not, that's pretty much all there is to it. Every program you've ever used, no matter how complicated, is made up of instructions that look more or less like these. Thus, we can describe programming as the process of breaking a large complex task into smaller and smaller subtasks until the subtasks are simple enough to be performed with sequences of these basic instructions. So I already went ahead and answered this question before starting the recording. So a program is a sequence of instructions that specifies how to perform a computation. It is just step-by-step instructions that the computer can understand and execute. Programs often implement algorithms, but note that algorithms are typically less precise than programs and do not have to be written in a programming language. All right, let's to what is debugging? Programming is a complex process. Since it is done by human beings, errors may often occur. Programming errors are called bugs, and the process of tracking them down and correcting them is called debugging. Some claim that in 1945, a dead moth caused a problem on relay number 70, panel F, of one of the first computers at Harvard, and the term bug has remained in use since. For more about this historic event, see first bug. Okay, see first bug. It takes us to a Wikipedia page, and there's the bug. It's really nice log. 800, something started. 1000, stopped. Failed special speed test. Relays changed. Start cosine t, sine check. 1100. 2025. First actual case of bug being found. 45 minutes after finding that. Arctangent started. 5 o'clock, close it down. Speed test. Arctangent. That's it. Okay, cool. So, I guess that's where they coined the term of computer being bugged if it wasn't working correctly. Moth found trapped between points at relay number 70, panel F of the Mark II Aiken relay calculator while it was being tested at Harvard University, September 9, 1947. Operators affixed the moth to the computer log with the entry, first actual case of bug being found. The term debugging already existed, thus finding an actual bug was an amusing occurrence. Neat. In 1988, a log with the moth still taped by the entry was in the Naval Surface Warfare Center Computer Museum in Dahlgren, Virginia, which erroneously dated it 9th of September 1945. The Smithsonian Institute's National Museum of American History and other sources have the correct date. Harvard Mark II computer was not complete until summer of 1947. So, yeah, the event cannot have happened in 1945. This is a featured picture on the Chinese language Wikipedia. Okay. Well, I can totally get distracted. Oops. That is for another day. Alright. 3 kinds of errors can occur in a program: syntax errors, runtime errors, and semantic errors. It is useful to distinguish between them in order to track them down more quickly. So according to Wikipedia, syntax error is an error in the syntax of a sequence of characters or tokens that is intended to be written in a program, in a particular programming language. Yeah, and then runtime errors, also known as program lifecycle phase, or execution time, is the final phase of a computer program's lifecycle. Oh, I see. So program lifecycle phase refers to what runtime is a part of. So this final phase of a computer program's lifecycle in which the code is being executed on the computer's central processing unit as machine code. In other words, runtime is the running phase of a program. A runtime error is detected after or during the execution running state of a program, whereas a compile time error is detected by the compiler before the program is ever executed. Neato. Semantic errors would be a form of logic error. It's interesting, these links redirect back to Wikipedia. I'm just thinking of maybe coming back to these specific terms and doing a report on each of those. It is useful to distinguish between them in order to track them down more quickly. So, comprehension question, debugging is A, tracking down programming errors and correcting them, B, removing all the bugs from your house, C, finding all the bugs in the program, D, fixing the bugs in the program. I'm gonna go with A, tracking down programming errors and correcting them. Programming errors are called bugs, and the process of finding and removing them from a program is called debugging. Next section, syntax errors. Python can only execute a program if the program is syntactically correct. Otherwise, the process fails and returns an error message. Syntax refers to the structure of a program and the rules about that structure. For example, in English, a sentence must begin with a capital letter and end with a period. The sentence contains a syntax error. So does this one. For most readers, a few syntax errors are not a significant problem, which is why we can read the poetry of E.E. Cummings without problems. Python is not so forgiving. If there is a single syntax error anywhere in your program, Python will display an error message and quit. You'll not be able to complete the execution of your program. During the first few weeks of your programming career, you'll probably spend a lot of time tracking down syntax errors. However, as you gain experience, you'll make fewer errors and you will also be able to find your errors faster. Which of the following is a syntax error? A, attempting to divide by 0. B, forgetting a colon at the end of a statement where one is required. Or C, forgetting to divide by 100 when printing a percentage amount. I would think it would be B, forgetting a colon at the end of a statement where one is required. This is a problem with the formal structure of the program. Python knows where colons are required and can detect when one is missing simply by looking at the code without running it. Who or what typically finds syntax errors? A, the programmer, B, the compiler or interpreter, C, the computer, or D, the teacher instructor. I went with compiler, interpreter. Option B, the compiler and/or interpreter is a computer program that determines if your program is written in a way that can be translated into machine language for executions. Next, we have runtime errors. The second type of error is a runtime error, so called because the error does not appear until you run the program. These errors are also called exceptions because they usually indicate that something exceptional and bad has happened. Runtime errors are rare in the simple programs you will see in the first few chapters, so it might be a while before you encounter one. Which of the following is a runtime error? A. Attempting to divide by 0. B. Forgetting a colon at the end of a statement where one is required. Or C. Forgetting to divide by 100 when printing a percentage amount. I'm going to go with A. Attempting to divide by 0. Python cannot reliably tell you if you are trying to divide by 0 until it is executing your program. For example, you might be asking the user for a value and then dividing by that value. You cannot know what value the user will enter before you run the program. Who or what typically finds runtime errors? A, the programmer, B, the interpreter, C, the computer, or D, the teacher instructor. So it would be the interpreter. If an instruction is illegal to perform at that point in the execution, the interpreter will stop with a message describing the exception. Next, we have semantic errors. The third type of error is the semantic error. If there's a semantic error in your program, it will run successfully in the sense that the computer will not generate any error messages. However, your program will not do the right thing, it will do something else. Specifically, it will do what you told it to do. The problem is that the program you wrote is not the program you wanted to write. The meaning of the program and semantics is wrong. Identifying semantic errors can be tricky because it requires you to work backward by looking at the output of the program and trying to figure out what it is doing. So which of the following is a semantic error with the same 3 examples provided in the previous 2 sections? A. Attempting to divide by 0. B. Forgetting a colon at the end of a statement where 1 is required. Or C. Forgetting to divide by 100 when printing a percentage amount. So it would be C. This will produce the wrong answer because the programmer implemented the solution incorrectly. This is a semantic error. Which of or who or what finds semantic errors? A, the programmer, B, the compiler interpreter, C, the computer, or D, the teacher instructor. So in this case, you would have to double check on your own work as a programmer. You must fully understand the problem so that you can tell if your program properly solves it. So in this section, we're going over experimental debugging briefly. One of the most important skills you will acquire is debugging. Although it can be frustrating, debugging is one of the most intellectually rich, challenging, and interesting parts of programming. In some ways, debugging is like detective work. You are confronted with clues, and you have to infer the processes and events that led to the results you see. Debugging is also like an experimental science. Once you have an idea of what is going wrong, you modify your program and try again. If your hypothesis was correct, then you can predict the result of the modification, and you take a step closer to a working program. If your hypothesis was wrong, you have to come up with a new one. As Sherlock Holmes pointed out, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. From the sign of war, story written by A for Arthur Conan Doyle. For some people, programming and debugging are the same thing. That is, programming is the process of gradually debugging a program until it does what you want. The idea is that you should start with a program that does something and make small modifications, debugging them as you go, so that you always have a working program. For example, Linux is an operating system kernel that contains millions of lines of code, but it started out as a simple program that Linus Torvalds used to explore the Intel 80386 chip. According to Larry Greenfield, one of Linus's earlier projects was a program that was switched between displaying quadruple A and quadruple B. This later evolved to Linux. This information was drawn from the Linux User's Guide Beta version 1. Later chapters will make more suggestions about debugging and other programming practices. For now, we have a question. The difference between programming and debugging is A, programming is the process of writing and gradually debugging a program until it does what you want. B, programming is creative and debugging is routine. C, programming is fun and debugging is work. Or D, there's no difference between programming and debugging. So according to what we just read, the answer is A. Programming is the process of writing and gradually debugging a program until it does what we want. Programming is the writing of the source code, and debugging is the process of finding and collecting all the errors within the program until it is correct. Next section, formal and natural languages. Natural languages are the languages that people speak, such as English, Spanish, and French. They were not designed by people, although people try to impose some order on them. They evolved naturally. Formal languages are languages that are designed by people for specific applications. For example, the notation that mathematicians use is a formal language that is particularly good at denoting relationships among numbers and symbols. Chemists use a formal language to represent the chemical structure of molecules, and most importantly, programming languages are formal languages that have been designed to express computations. Formal languages tend to have strict rules about syntax. For example, 3 plus 3 equals 6 is a syntactically correct mathematical statement, but 3 equals +6 $sign is not. But H2O is a syntactically correct chemical name, but 2 capital Z lowercase z is not. Syntax rules come in two flavors, pertaining to tokens and structure. Tokens are the basic elements of the language, such as words, numbers, and chemical elements. One of the problems with 3 $sign +6 $sign is that $sign is not a legal token in mathematics, at least as far as we know. I think that means I got an email. I realized I moved too much in the previous recording, so I'm really trying to stay still. It's ironic that I have a hard time staying still when my name is Jo. Alright. Similarly, the subscript 2, capital Z, lowercase z, is not legal because there's no element for the abbreviation ZZ. The second type of syntax rule pertains to the structure of a statement, that is, the way the tokens are arranged. The statement 3 equals plus $6 is structurally illegal because you can't place a plus sign immediately after an equal sign. Similarly, molecular formulas have to have subscripts after the element name, not before. When you read a sentence in English or a statement in a formal language, you have to figure out what the structure of the sentence is, although in a natural language, you do this subconsciously. This process is called parsing. For example, when you hear the sentence, "the other shoe fell," you understood that the other shoe is the subject and fell is the verb. Once you have parsed the sentence, you can figure out what it means, or the semantics of the sentence. Assuming that you know what a shoe is and what it means to fall, you will understand the general implication of the sentence. Although formal and natural languages have many features in common, tokens, structure, syntax, and semantics, there are many differences, such as ambiguity. Natural languages are full of ambiguity, which people deal with by using contextual clues and other information. Formal languages are designed to be nearly or completely unambiguous, which means that any statement has exactly one meaning, regardless of context. Redundancy is another characteristic in which formal and natural languages differ. In order to make up for ambiguity and reduce misunderstandings, natural languages employ lots of redundancy. As a result, they are often verbose. Formal languages are less redundant and more concise. Literalness. Formal languages mean exactly what they say. On the other hand, natural languages are full of idiom and metaphor. If someone says the other shoe fell, there is probably no shoe and nothing falling. Okay, tip. You'll need to find the original joke to understand the idiomatic meaning of the other shoe falling. Yahoo Answers thinks it knows. I thought the other shoe falling was another way of saying like a pin dropped or something shocking. I could be completely wrong. People who grew up speaking a natural language, everyone, often have a hard time adjusting to formal languages. In some ways, the difference between formal and natural language is like the difference between poetry and prose, but more so. And if anybody knows what the idiomatic expression of the other shoe falling means, please comment. And yeah, I wonder what the origin of that phrase is too, because I always find those kind of linguistic histories very fascinating. poetry. Words are used for their sounds as well as for their meaning, and the whole poem together creates an effect or emotional response. Ambiguity is not only common, but often deliberate. Prose, the literal meaning of words, is more important, and the structure contributes more meaning. Prose is more amenable to analysis than poetry, but still often ambiguous. On the other hand, we have program. The meaning of a computer program is unambiguous and literal, and can be understood entirely by analysis of the tokens and structure. Here are some suggestions for reading programs in other formal languages. First, remember that formal languages are much more dense than natural languages, so it takes longer to read them. Also, structure is very important, so it is usually not a good idea to read from top to bottom, left to right. Instead, learn to parse the program in your head. You identify the tokens and interpret the structure. Finally, the details matter. Little things like spelling errors and bad punctuation, which you can get away with in natural languages, can make a big difference in a formal language. Here we have a couple quiz questions. The difference between natural and formal languages include: A. Natural languages can be parsed, while formal languages cannot. Can rule that one out. Option B. Ambiguity, redundancy, and literalness. That would be the right answer, but let's continue. Option C says there are no differences between natural and formal languages. That would defeat the whole point of this section. And D. Token, structure, syntax, and semantics. Those are characteristics across both natural and formal languages, so we can eliminate that answer. So the correct answer is ambiguity, redundancy, and literalness. All of these can be present in natural languages, but cannot exist in formal languages. True or false? Ooh, these are always a weak point for me. True or false questions. Yeah. Still getting used to it. Reading a program is like reading other kinds of text. That would be false, because reading a program requires a different level of parsing out tokens. Requires a more active reading mindset, I think, because like reading through a novel, you can kind of passively pass over the words and sentences, and certain details stick out, and then contextually pull the whole thing together. So it's false. Yes. Reading a program is not like reading other kinds of text. It usually takes longer to read a program because structure is as important as the content and must be interpreted in smaller pieces of understanding. Does anybody else have issues with like true or false questions? Like, I would rather write an essay than stress over a true or false question. A typical first program. Traditionally, the first program written in a new language is called Hello World, because all it does is display the words Hello World in Python. Source code looks like this right here. So yeah, print, and then parentheses, quotation of hello, comma, world, exclamation. So this is an example of using the print function, which doesn't actually print anything on paper. It displays a value on the screen. In this case, the result is the phrase, hello world. So it's essentially giving a command to the program. Print. Kind of like telling a dog, speak. Speak. Yeah. So print what? Hello. There we go. Here's the example in active code. Give it a try. So here we already have print hello world. Save and run. Hello world. Show encodings. Really simple. And hello world and the output. The quotation marks in the program mark the beginning and end of the value. They don't appear in the result. Some people judge the quality of a programming language by the simplicity of the Hello World program. For the standard, Python does about as well as possible. Print function A sends information to the printer to be printed on paper. B displays the value on the screen. C tells the computer to put the information in print rather than cursive format. Or D tells the computer to speak the information. So the answer would be B, displays the value on the screen. All right. Next section. Comments. As programs get bigger and more complicated, they get more difficult to read. Formal languages are dense, and it is often difficult to look at a piece of code and figure out what it is doing or why. So what do they mean by formal languages are dense? Well, for the operation of addition, let's say, you have one character or one token that's a plus sign. But in our natural language, we can either say add or plus, and those are 4 characters to 1. So that entire word and the value of those 4 characters in that sequence is condensed into one symbol. So it's often difficult to look at a piece of code and figure out what it is doing or why. For this reason, it is a good idea to add notes to your programs to explain in natural language what the program is doing. These notes are called comments. A comment in a computer program is text that is intended only for the human reader. It is completely ignored by the interpreter. In Python, the hashtag token starts a comment. The rest of the line is ignored. So here in our active code window, we have a new version of Hello World. Here on lines 1 through 5, all of this text is preceded by a hashtag on each line or £. This demo program shows off how elegant Python is. Written by Joe Soap, December 2010. Anyone may freely copy or modify this program. And then line 7, we have the print function, followed by £. Isn't this easy? That will not show up in the output. Let's test that. There we go. output only says hello world. So if we show the code lens to go through these lines, there's only, you can see here we have 7 lines of input into the program. However, Python only recognizes one step on line 7. Notice that when you run this program, it still only prints the phrase hello world. None of the comments appear. You'll also notice that we've left a blank line in the program. Blank lines are also ignored by the interpreter, but comments and blank lines can make your programs much easier for humans to parse. So you can use them liberally. It's not going to affect the execution in the program. So here we go. What are comments for? A, to tell the computer what you mean in your program. B, for the people who are reading your code to know in natural language what the program is doing. C, nothing, they're extraneous information that is not needed. D, nothing in a short program, they are only needed for really large programs. So the comments would be for the benefit of option B, people who are reading your code to know in natural language what the program is doing. Yeah, to just give other human beings who would be reviewing the source code some sense of familiarity. But yeah, check. Let's see what it says here. The computer ignores comments. It's for the humans that will consume your program. So we have this workspace. You can use this active code to try out anything you like. So print chill, just chill. Boop. There we go. All right, so we are reaching the conclusion of Module 1. So here we have a glossary of terms that we discovered throughout the sections of this module. So I'm thinking of some ideas of how to do this in a more interactive way for myself and for anybody that ends up following along to this video. So I will link those activities in the description. I'll most likely be flashcards with multiple choice and online quizzes for participation. But yeah, if you have any ideas, please feel free to email the channel or put in the comments below. And there's no exercises for this first module. But as we go forward, we'll have more opportunities to practice all of the operations and functions that we've learned. So, anyways, thanks for watching, and keep calm, and we'll stay chill. All right. Please let me know how I did. This is really a big leap from isolation. So, anyways, see you soon.